All right. Hi, everybody. I'm Julian. If you don't know me, I'm your TA this semester for machine learning. I have the privilege today of giving a lecture on a really fun topic, logistic regression, which I believe is also kind of an introduction to classification problems within the class. So I want to preface this by saying, if you have any questions whatsoever, please feel free to email me, come to my office hours, my TA sessions, my tutoring hours. I would be more than happy to help out, answer any questions. So I know, bear with me, I'm not a master like Professor Kapikoff, but hopefully you can leave today learning a thing or two. So without further ado, just, the agenda for today. The first thing that I want to do is just kind of motivate the question of, well, why classification? Why do we need logistic regression, right? And by this, we're going to finally introduce the idea of what's a regression problem versus what's a classification problem, right? When you use one technique over the other. Then we're going to finally start to build our intuition behind logistic regression. All right. Why do our linear models, right, what you guys learned last class with just basic linear regression, why does that not transfer over well when we have a dependent variable that is not quantitative? After we do that, the goal is to then formalize this intuition, right? Is there a formula? Is there a model that kind of captures this intuition really well and kind of reinforces it? Spoiler alert, there is. And then the fourth thing we're going to do is interpret our model, right? So those are just the 4 steps for today. Before we get into any of that, I just want to do a quick refresher so that this comes to the forefront of our minds when we do this, right? I just want to quickly refresh our minds on the definitions between probability and odds and the relationship between the two, right? So just for instance, right, the probability of drawing an ace out of a deck of cards is 4 divided by 52, right? 4 just being that there's 4 aces in the deck and there's 52 cards in the deck. Plain and simple. The odds is just 4 over 52 minus 4. So 4 over 48. We can kind of decompose this a little bit and then just say generally that the probability are the odds over 1 plus the odds. And similarly, we can kind of work this around and say, all right, the odds is just equal to a probability over 1 minus the probability. So I just kind of want to have that, in our minds as we go into this, because I think a lot of logistic regression really hinges on our ability to understand probability and odds and kind of the relationship between the two. It'll become much more apparent within the next few minutes. So, yeah. So now to move on to classification. The first question that comes to mind is, what does it mean to have a classification problem? Well, there are 2 kinds of problems that we're going to ask in this class. You guys answered one of them last class, which is, what do we do when we want to predict an outcome where the outcome is a quantitative variable, right? So for instance, this is our y variable. This is our independent variable. Y is quantitative, meaning it's a continuous variable. It can, like, income, age, salary, This is what we would do, right? As you guys covered in last class, what we do, one of the things we can do, I should say, is, all right, we can plot the points and then just find a line of best fit that minimizes the squared residuals. And that was linear regression, right? That is with a quantitative dependent variable. But today, what we're going to do is we're going to say, all right, but what if the outcome we're trying to predict is not quantitative? i.e., what do we do if our dependent variable is categorical? That is what we call, in data science, a classification problem. Today, we're going to specifically focus on what do we do when our outcome variable only takes the value 0 or 1, right? The event did happen, it didn't happen, yes, no, 1, 0, so on and so forth, right? Just 2 levels. You'll often hear a dependent variable with only 2 levels called a dummy variable an indicator variable, a binary variable, they all mean the same thing, right? So just in case you hear that terminology, we're all talking about the same thing here. Something will come to mind just looking at this picture that we might have a problem, right? In the case before, we had a quantitative dependent variable. Our outcome could take various outcomes, right? Someone's age could be 68, it could be 72, it could be 54, so on and so forth. But now, y can only take two variables. Either the event did happen or it didn't happen. And so right now, the next thing we're going to do is kind of develop the intuition. Well, what we know right now, the only tool that we've gone over in this class is just fitting a line through this model, finding a line of best fit. So what we're going to do now is, all right, well, let's do that. Let's try to fit a line through here and see where the problems and the issues arise. All right. So what I've done is I've basically set things up like we would approach this problem, just knowing everything we've gone over in the class. Meaning, we have a binary dependent variable. In this example, we can just predict whether or not somebody's going to get into Wesleyan. That takes value 1 if they get into Wesleyan, 0 they don't get into Wesleyan. Our y-axis is the probability they get in, right? Of course, if somebody gets in, the probability we observe is 1, they do get in, 0, they didn't get in. And what I did is I just fit a line through this, right? That's intuitively what we would do right now. We haven't been introduced to anything else. So this is the setup. And I want to point out a couple issues that arise when we just try to apply this linear regression way of thinking to a classification problem. So the first one being, what do we do if this variable x, now we can think of x as kind of a composite score, right? Applications have many different, are multifaceted, right? They have many different factors that go into it. We can just think of a composite score x here. What do we do if on our test data, right, after we train our model, what do we do if we get a person whose score is greater than 50 or it's less than -50? This is just a mathematical issue that comes to mind immediately. Well, the probabilities we would be getting would be above 1 or below 0. As x approaches infinity, the value of p is going to increase and it's going to go above 1, which intuitively and mathematically should probably start ringing alarms in our head. But I would even argue that this is very important, but I think the more important issue here kind of helps us develop this intuition behind logistic regression. And that's the fact that if we look at this line of best fit, the rate of change, the slope, is equal throughout. And I kind of want to take a second and just think about, well, what does that mean? Well, let's say we're confident with our information that somebody's going to get into Wesleyan, right? They have a composite score of 48 and they go up to 50. Well, we were already pretty certain that they were going to get in. Their probability was already pretty high. So that shouldn't really change whether or not we predict the person's going to get into Wesleyan, right? Same thing if they have a really low score to begin with. But what I want to raise our attention to is, what if we're in the middle? I really like to think of this idea, right? If x is 0 and our probability is 1/2, that means at this point, we have no information that sways us in one direction or another of whether or not somebody is going to get into Wesleyan. When we think of it this way, each additional bit of information has huge sways on our prediction. Meaning, in relative terms, a 2-unit increase here is going to have a much bigger effect on the probability our predicted probability of somebody getting in than if they're already all the way on one end of the scale. So just to think of what does this mean, right? How can we kind of make a function that kind of aligns with this intuition? We would maybe expect there to be a jump, right? Something of this sorts, right? Something along those lines, maybe. Where once we get information where we were previously very uncertain, it was, ambiguous to us. Now, little bits of information in relative terms have big effects on our prediction. Similarly, kind of what we were talking about to begin with, if we're already pretty certain that they're going to get into Wesleyan, small changes aren't really going to do all of them. We already have evidence that pushes us in one way. So we would maybe expect a sort of leveling out kind of around here, maybe something of those sorts. And likewise down here, right? Maybe something like this, maybe like that. And if we try to connect this together, we're going to get a function that kind of takes this shape, right? It's going to go up, and it's going to go there. It's going to go up, it's going to go there. Oh, mother of pearl. Okay, sorry. Wait 1 second. Well, we may have sacrificed the linear line a little bit, but it doesn't matter. We shouldn't use a line of estimate for this anyways. So what we'll essentially get is something that takes the shape of the green line. What does this green line mean? What does it mean mathematically? It takes this shape. Now, I'm going to be brutally honest with you. When I see that formula, I couldn't tell you what's happening. I have no idea what's happening. But the beautiful thing is we've already developed the intuition behind what's happening, right? We know that small jumps here are going to have big changes on our prediction, as opposed to when we already have evidence pointing us in one way or another. So let's plug in some numbers, right? Let's see how this function in green, which is the same as this equation here, remedies these two issues that we see when we apply our techniques from linear regression to a binary classification problem. The first thing I want to point our attention to, addressing the first problem, is, all right, we have our composite score x. What happens as x approaches infinity, right? Let's just plug infinity in here, right? Infinity over e to the infinity over 1 plus e to the infinity. What does that mean? It means that we expect, as x approaches infinity, that our probability is going to get close, is going to approach 1. If we plug infinity in, we're going to get 1. Likewise, if we put in negative infinity, as x approaches negative infinity, our probability is going to be close to 0. And the really interesting thing here, which we'll get into in a second, but what if x is 0? 1 over 1 plus e to the 0, 1/2. Which brings us right here. And so if you want to take a second, just make sure that this all kind of makes sense in your head, right? That's perfect. What I'm going to do next is I'm just going to take this formula one step further. Why is that? I know a lot of people are more mathematically oriented, right? When they see math that reinforces the intuition, kind of like how we did here, it really helps them out, right? That's the case for me. And so I thought if it even helped one person out, the value added was worth it. So what I'm just going to do is I'm going to take the derivative of P with respect to our composite score of X. And the beautiful property of this function is that it just gives us the probability times 1 minus the probability. Now, that might not mean anything to you, and that's perfectly okay. But I just want to remind us that we can think of this as the rate of change at a point, right? The instantaneous rate of change at a point. And if we have built our intuition around the idea that when we have no information that tells us whether or not someone is going to get in or not going to get in, that we have big relative one unit increases are big in relative terms on our predictions. And that's exactly what we see here. If X is 0, that is the highest rate of change that we will observe. And it will be 1/4. And that exactly captures what we've been talking about, that this is a much higher jump than when we're already very confident that somebody is going to get into Wesleyan. It levels out over here. The jumps are massive over here, relatively speaking. So if what I just said is gibberish, it doesn't resonate with you, don't worry about it, right? My goal was to just develop our intuition. If this makes sense, perfect. That's the goal. I just wanted to reinforce this intuition more formally with math because I know it helps some people. And I think it's nice to see how we get our formulas instead of somebody saying, all right, our y values are here, our x values are here, and this is the function we use, right? We just trust them on a whim. We didn't derive this, but we had a basic idea of what's happening, and we saw a formalization of it with math. And I think that's the big thing. All right. So now what I've done is I just want to write out the model that we talked about last class, which is just multiple regression, right? If you've ever taken a class with Professor Kaparakis, you know that one of the most important things in statistics or data science is you need to know where you are and where you want to be. And this is what we want our equation to look like in the end. This is where we are right now. So we have the probability of X is equal to e to the, and then our function, over 1 plus e to our function. This is where, the tricks that we talked about earlier on in class really become handy dandy, right? What we're going to do now is we're going to slowly just start to deconstruct this from probabilities to odds to log odds, and we're going to get to where we want to be. So as I said, now we're in a world of probabilities. What we can do is then just take the odds, and that removes our denominator. And this is exactly what we see over here. Now we have everything that we want, but it's e raised to that. So what do? We take the log. Logs are beautiful for many reasons. This is one of them. What we have now is the equation that we want, that we can interpret. Kind of. The thing that I want you guys to remember, and that we'll keep on, trying to sear into our minds, is the fact that when we run logistic regression, right? This is the formula. We're working in log odds. I'm going to say that one more time. Our coefficients, beta 1 until beta k, where k is just the number of predictors you have, is in terms of log odds. Now, you might be wondering, well, okay, this kind of checks out, but how do we get it so that our machine tweaks our sigmoid function, the function that we were talking about before? Sorry, I'm not sure if I had said this formally, but the function that we had described as p of x is equal to 1 over 1 plus e, sorry, 1 plus e to the negative x is called the sigmoid function. You also hear some people call it logistic function, whatever it may be. How do we get our machine to tweak this so that we get the best sigmoid function? We can kind of go back, right? A similar question for linear regression is, how do we get the line of best fit? And we did that by minimizing the squared residuals, the sum of squared residuals. When it comes to logistic regression, we do something called the maximum likelihood. We want to maximize likelihoods. I think that this is a whole nother video, and I would argue that we don't even need to worry about that too much right now. My goal is just to build our intuition and a basic rudimentary understanding of classification that we can then build off of as the semester goes. But I would highly recommend watching a video from StatQuest or Ritvikmath. They're both very good, and they'll be able to explain this much clearer and much more depth very quickly. But a basic idea of maximum likelihood is we observe that these people get into Wesleyan, these people don't get into Wesleyan. How can we make a function that maximizes the likelihood such that people that we would predict for people that did get into Wesleyan, that their probabilities of getting would be very high. And for people that didn't get into Wesleyan, how can we tweak our model such that the ones who didn't get into Wesleyan have low probabilities? That's all we try to do, is we try to maximize the likelihood of the predicted probabilities matching the actual outcomes. That's just plain and simple. That's all we're trying to do here. If you want a more complex, complicated, more in-depth walkthrough of it, highly recommend watching another video. But the reason why I do bring this up is because our log odds, what we have here, is used in order to tweak our sigmoid function, right? What basically happens is that these values get plotted onto a line. We tweak the line. We convert the log odds back to probabilities. We calculate the likelihoods. And then the line that then gives us the sigmoid that maximizes the likelihoods the best is the final sigmoid function we get. If none of that made sense, don't worry about it right now. I just know that a lot of people like to understand, how do we get, our best line, our best function within logistic regression? How do we tweak it? So linear regression, we minimize the sum of squared residuals. Logistic regression, we maximize the likelihood. That's all that's happening. All right. So what we've done so far is we've discussed the difference between regression and classification, right? Predicting a quantitative outcome versus a categorical outcome. We've built our intuition for logistic regression, why we can't just set a linear line. We've used some math to kind of formalize this intuition, right? Actually put it into an equation that reinforces exactly what we were diagnosing as the issues with fitting a linear model to a binary outcome. Which takes us to our last goal for today, and that's we want to interpret the model. This is always very, very important, right? Because if you can't interpret your model, what's the point? But it's especially tricky with logistic regression because I want to remind you that everything is in terms of log odds. All our coefficients are in log odds. So to run us through an example to understand what's happening and how to interpret what's happening, I just built out a basic equation. Our y-intercept is -9. I wouldn't worry about that for right now. The points of interest are x1 and x2. x1 is just some independent variable, x2 just some independent variable. We'll call them quantitative right now, so we can just say, you know, 1 unit increase in x1 or x2, right, so on and so forth. When we run our model in R, we're going to get this, just what I've written up here. And we're going to see that a 1 unit increase in x1 decreases the log odds by a factor of 0.116. Now I want to think about what that means. What does the log odds decreasing by 0.116 mean? I couldn't tell you. I could not tell you. You cannot interpret this. Well, okay. If you can interpret this, you deserve the Nobel Prize. But I cannot interpret this. And I don't think a lot of people can interpret this. Right? Understanding coefficients and log odds, you know, unless you have a calculator for a brain, we're just not going to be able to do it. Right? It's kind of like when you have a candy bar, right? You know how behind like all the candy bars, you know, Snickers, Milky Way, all these things, you have that one ingredient, nougat. I have no idea what nougat is. I have no idea how to interpret log odds. It's, you know, kind of the same thing. So what do? We exponentiate our coefficients. We're kind of reverse engineering and decomposing what we have here to get us what we want. So, all right, we exponentiate our coefficients. E to the, you know, negative 0.116 gets us 0.89. Similarly, you know, e to the 0.565 gets us 1.76. Since we've just taken e to the log odds, we don't have to worry about the log anymore. We're operating in odds from now on. So these are our odds. What does this mean? What does it mean that a 1 unit increase in x is associated with a change in the odds of y of a factor, multiplicative factor, of 0.89? Well, the important thing to remember is that your odds, when you're interpreting these coefficients, are always, always, always relative to 1. Always. So, if the coefficient here was 1, the odds of y happening don't change whatsoever from a change in x. But if the coefficient is 0.89, since it's relative to 1, let's take 1 minus 0.89, and we get negative, oh my lord, sorry, we get 0.11. What does that mean? That just tells us that the odds of y happening, the odds that somebody gets into Wesleyan, decrease by a factor of 11% when x1 increases by 1 unit. Somewhat similar to our interpretation for linear regression, right? A change in x1, a 1 unit change in x1 in linear regression is associated with a beta 1 change, unit change in y. It's just odds, and it's relative to 1. The second thing is when we go to x2, when we exponentiate the coefficient, we get 1.76. So what does that mean? Well, it's relative to 1, meaning that this minus 1 is going to get us 0.76. i.e., this is 0.11 below 1, this is 0.76 above 1. In this case, that means that since the odds are greater than 1, the odds of y happening increase by 76% when x2 increases by 1 unit. I'll let that, sit for a second so everybody can just digest it. But that's all that's happening here. We're in log odds. So we exponentiate our coefficients. And then our coefficients are in odds, meaning that it's just relative to 1. That's it. It's 0.89. So we know that if x1 increases by 1 unit, the odds of observing y happening decrease by 11%. And that's it. That's the lecture for today. I know this kind of takes a second, right? I know at first it's a little hard to kind of grasp everything and piece everything together, right? I know it's a lot of information, but what you guys covered last class with linear regression and what we just covered with logistic regression are really the building blocks for all the models that we're going to build throughout the rest of the semester, right? One of them being a regression problem, things like today being a classification problem. So just to recap, what did we do? Well, we addressed the fact that there are two kinds of problems that we want to predict in machine learning. One of them where the dependent variable is quantitative, income, salary, age, weight. The other one is a classification problem. With specifically today, a binary dependent variable. But classification in general is just a categorical dependent variable. This can be, such as today when we did a binary dependent, that can be the person is going to get cancer or they're not going to get cancer. They're going to suffer a heart attack, they're not going to suffer a heart attack. They're going to get into Wesleyan, they're not going to get into Wesleyan. These are the things that we're trying to predict. And what we then did is we said, all right, well, we need more tools in our toolbox to answer these kinds of questions, right? Just applying the tools we had from linear regression doesn't really work well. One of the reasons being, well, what if we could have a probability above 1 or below 0? We need something that's bound between, that can go from negative infinity to infinity, and the probabilities are bound between 0 and 1. But I would argue that the equally, if not more important issue is that we realize that when we don't have much information, when the probability is 1/2 and our score is 0, small changes around there have big impacts, relatively speaking, on our prediction of whether or not someone is going to get into Wesleyan or they're not going to get into Wesleyan. Whereas if they have an SAT score of a 1570 and it goes to a 1590, we already would have imagined that they would have gotten in. So those small changes at one extreme end doesn't really change our prediction. What we then did is we formalized it with math, right? We showed that exactly this kind of intuition that we just talked about can be captured by this function right here. Known as the sigmoid function. I will mention that this is going to be an important function at the end of the semester when you guys get to neural networks. With neural networks, you have to choose a kind of loss function that you want. This is a very popular one. exactly for the reason that we actually talked about, which is the fact that when you take the derivative of it, it's the same thing as the probability times 1 minus the probability. And what that showed us today is exactly what we were talking about, is the fact that these small jumps where previously we have no information can have large effects on our predictions of Y happening or not happening. And then we interpreted our model, right? We started off with the probabilities. We used some very nice properties to go from probabilities to odds to finally log odds. And then we saw that when we ran our model, everything we have is in terms of log odds, which really aren't interpretable. So what we did is we exponentiated the coefficients and we interpreted them relative to 1. Just for, it can't hurt, for one more time's sake. When we exponentiated this coefficient, we got a coefficient of 0.89. And since it's relative to 1, since it's 0.11 below 1, we then found out that the odds of Y happening, the odds of somebody getting into Wesleyan, decrease by 11% for each 1 unit increase in X1. And that's it. And that's all. I want to say one more time that if you have any questions whatsoever about anything that I just covered today, I would love for you guys to email me. Never hesitate. I'm very available, very accessible. And I really look forward to the semester ahead. I know I may not explain things as well as Professor Kapikoff, but I tried, and I hope this kind of at least helped us understand why we need logistic regression, or rather why we can't just use our tools from the linear toolbox to answer classification problems. So thank you guys, and I'll see you next time.